Thank you for the lights. Welcome to my presentation called Finding Other Worlds. In this presentation, we will talk about the location of our solar system, Kepler Space Telescope, specific methods used to find other planets, new planets we have found, planet conditions necessary for habitability, solar systems with habitable planet candidates, moons of Jupiter and Saturn, center of our Milky Way. We live on a small-sized planet, in an average-sized solar system, in an average-sized solar neighborhood, in an average-sized galaxy, in an average-sized local group, in an average-sized local superclusters in the observable universe. Our Milky Way galaxy is a collection of 200 billion stars. It is 120,000 light years across. 1 light year is 6 trillion miles. It is a barb-shaped or spiral galaxy. And we are 26,000 light years from the center, or big area in the middle. And we live in the Orion spur, sandwiched between the Perseus arm and the Sagittarius arm. Our local neighborhood consists of small dwarf galaxies, and we also have, our sister galaxies, which is Andromeda Galaxy, which is 2.1 million light years from us, consists of 1 trillion stars, and the Pinwheel Galaxy, 21 million light years away. And this is a supercluster that we live in, one of countless of them. Today we're going to be talking about telescopes that have helped us find these new exoplanets and solar systems. The Hubble, the Spitzer, the Kepler in particular, the TESS, and the Webb that looks like this. JWST was online this summer. It is 1 million miles from Earth. It costs $10 billion and is able to see in the infrared, and is just putting material online now, and we'll be talking about some of the planets it has found. The Kepler Space Telescope mission launched in 2009 and was to survey a portion of the Milky Way to discover Earth-sized planets that exist in habitable zones near its host star. Its mirror was 4.5 feet in diameter, or 55 inches, and weighed 2,300 pounds with a Schmidt camera. It observed 500,000 stars and detected 2,600 exoplanets. Kepler mission ended in 2018, and it scanned a narrow, elongated pie-shaped segment of our galaxy that is 3,000 light years long in the Orion and the Sagittarius arm, going forwards toward the center. And it had a K2 mission. It conked out a bit in 2015, but they recalibrated to have a different measurement to do this, and it still got more information for us. And by the numbers, it's out 2,200 days in space with 2 different missions, 64 million miles away, trailing Earth around the sun, and has all these confirmed and candidate possible exoplanets. And just using 3 gallons of fuel, pretty efficient. Yeah. And the TESS, or Transiting Exoplanet Survey Satellite, is a space telescope that orbited Earth. Launched in 2018, its mission was to search for exoplanets for 2 years in an area 400 times larger than Kepler. Wide-field cameras scanned for prime targets like star systems of planets. It provided an all-sky survey for our transiting planets. 1991, there were no known exoplanets revolving around a star. By 2007, there were 193 found, 1,000 by 2015, and by 2022, with the help of Kepler, TESS, Hubble, and Webb, now over 6,000 found. To give the proper location of stars and their planets, we will mention the constellations they lie in. These constellations, from our point of view, appear to make a connect-the-dots picture of recognizable, universal known figures in the nighttime sky. However, the stars that make up these perceived patterns are all separated by tens of millions, or tens of trillions, and hundreds of trillions of miles from each other. So we might see a Big Dipper from our point of view, but when you get up there, they're just stars that are hundreds of trillions of miles from each other. Or you might see a shape in the sky that looks like this. They're all just stars that look from here, from this point of view, but when you go there, they're all separated by long periods. This tendency to make patterns when there is none is called perigeulia, like seeing a face on Mars when it's just a glacial moraine. To give proper locations, the Kepler Space Telescope revolutionized the way we planet hunt and was able to get the rough size or mass, temperature, and orbit distance of a planet candidate. Scientists interpreted Kepler's raw data by using 4 methods. First, the transit method, or a distant sun dips in brightness when a planet passes across its face as scanned by Kepler. That means there'll be a dip in the brightness of this host star. And with that dip in brightness, we can get the orbital period and the size, 1.0 being Earth, compared to our planet. So we get a dip in this because the planet transits the host sun's surface. And if we're looking at a solar system like the TRAPPIST-1 system, which we'll get to, Kepler would see this. For the host sun, or this right here, it would see a band. But it would be interrupted then by 7 planets that have distinct gaps, like the F and G planet, the C and B, where it transit across it, the D and the E, and it looks like this, a dip in brightness. So that's how we're able to tell what's going on. And also, secondly, is the Doppler method, or the tugging of a parent star by its planet to produce a telltale wobble to then ascertain planet mass, size, duration, and orbit. That is a radial velocity, which infers the existence of a planetary companion from its gravitational pull on its host star. Simply put, if you have a planet here, it'll influence its sun. And the sun then will have a wobble because each one produces a gravitational field. So this planet will produce a wobble with the sun. A wobble going away from us is called redshifted, or shifted to the red away from us. And a planet going toward us is shifted toward the blue, or blue shifted, where the rays of light are short. They're blue. Redshifted, all redshifted means when you see a sunset or a sunrise, it's a bit red. There's a reason for that, because of the sun's rays. And once again, this is what the wobble will look like, going toward us, away from us, toward us, away from us, and the dip of the planet, brightness of it. There's also chemical signatures to know. The light that passes through a planet's atmosphere can be analyzed to ascertain its chemical elemental composition using spectroscopy. The elements will tell us, for example, if hydrogen and oxygen are in it to be able to produce water, H2O, or CO2, carbon dioxide, or ammonia, NH3, or methane, CH4, or sulfuric acid, H2SO4, or sulfur dioxide, SO2. So that's how we know what the chemical composition of these atmospheres are. In the Milky Way galaxy, or in any other 2 trillion galaxies, there are more planets than stars. There are tens of billions of planets and star systems in our galaxy alone. The majority of the planets found thus far, or 3/4 of them found, are super Earth-sized ones, twice as big in diameter and twice as heavy as Earth. So our planet's about here. But most of what we're finding outside of our solar system are planets that are about 1.5 times the size of our planet, and the majority of them are between 2 and 2.5 times the size of our planet. And an exoplanet, by the way, is a planet that orbits a sun-like star outside our solar system. So if we're finding planets, they're usually more robust than ours. The first one found was 51 Pegasi b, or Bellerophon. It's 48 light years away from Earth in Pegasus. And it's an exoplanet that was found in 1995, orbiting just 5 million miles from its sun. So therefore, when it's that close to the sun, it's very hot. And this is a hot gas giant, kind of like Jupiter. That is, it's a gas, very large, hot gas giant, and about half the size of Jupiter. And it would look like something like this. It was originally formed far from its star, but migrated over time toward it. The closest planet we have toward us is in the Alpha Centauri system, which is 4.2 light years away from us, or 25 trillion miles. And in that system, there'll be 3 suns. Compared to our sun, there'll be the Alpha Centauri A, a larger size than our sun, Alpha Centauri B, a bit smaller than our sun, and a red dwarf sun, which is a small star called Proxima Centauri. And around Proxima Centauri is a small planet called Proxima B. B stands for the planet. That orbits this red dwarf star once every 11.5 days, and this star gets very hot. The closer it is to this host star, the hotter it is, the more uninhabitable it would be, by the way. And this would get 300 times the amount of sunlight that we do, and it would kind of look like this, standing on the planet there. That's the closest one. There's other ones, OGLE or OGLE or 2016. They call that HOP. We can excuse the Star Wars references here. Everybody gets excited about that. It's 21,000 light years away from Earth and Scorpius. It is 13 times the size of Jupiter's mass, which means it's a very large gas giant. It orbits a cool red dwarf star every 10 years. So it's very far away from its star, which means it's very cold. It takes a long time to orbit around it. And it's negative 370 degrees on this planet, which makes it as cold as Pluto. But it is a gas giant, and gas giants don't have a surface to stand on. As you go down in them, there's more atmosphere, particularly of hydrogen, and you get more pressure, you start getting squashed, and it starts getting hotter as you go inside of it, but no surface. So they're not clear about this one. It's a bit of a mystery. And then there's Kelta 1b, is a brown dwarf planet gas giant transiting a mid-F star, which I'll explain, and is just about 2 million miles from its sun. Okay, so this needs a lot of explanation. Our sun is a G-type star, a mid-range, middle star in terms of size. We saw a smaller star with that red dwarf in Alpha Proxima, and then there are larger stars, and this one orbits an F-type star, which is about 1.3 times the size of our sun, a bit larger. And it's very close in, which means it's pretty hot there. That's what we get from that. It's located in Andromeda, and it's about 30 times heavier than Jupiter. It has a crushing surface pressure as you go down into it, and it's strongly irradiated. It gets 6,000 times the amount of sunlight that Earth does. And it's like a hot Jupiter. It's made of metallic hydrogen, and it's 4,000 degrees. It was found in 2012. So these are not good conditions for habitability when you're that close for anything like that, or having water on it. This is my favorite one. This is J1407b. This is an exoplanet that's 420 light years away in Centaurus. And what this is a giant planet here, and it's so big it's called a brown dwarf. A brown dwarf is like a very big gaseous planet, but it's 75% the size of our sun, but doesn't have enough hydrogen in it to make it into a sun, to fuse hydrogen into helium to make sunlight and heat. So it's like a big gas giant, and around it has a ring system that really goes out far, like 20 million, outward of 120 million miles, and that's really far. The ring system is from a moon that got too close to the gravitational effects of this gas giant, and it has 30 rings on it, and each ring has separation, which means it has a shepherding moon in between each of these. So it has probably 100 moons on it. And what this is made out of is ice and rock material about the size of your fist, about the size of your body, about the size of a car, and they all orbit around it. Just like on Saturn. And in Saturn's B ring, they have mountains on it from all this ice materials that are 3 miles tall, and you can see the shadows of them right here. So imagine having a ring system on a planet that's 1 billion miles away that Saturn is, or with the case of this one, is 10 quadrillion miles away. I think that's absolutely stuns me, actually. This is K218b. K218 would be the sun, and the B would be the planet. and it's an exoplanet in Leo, and it's 8 times the size of Earth, so it's like about a Neptune-sized planet. And it's 110 light years away from us. And what's significant about it, and why I'm showing it to you, is because in its atmosphere, water vapor has been detected at rates of 1 to 50%, and maybe on its surface, but we can't tell. Its sky is full of clouds where water collects and could rain, or might have an ocean surface on it, but we're not clear. It takes 32 days to orbit its M-class star, a bit smaller than our star. So it's warm, that's why it's able to produce water on it in its atmosphere. And they're able to find hydrogen, helium, and oxygen on it. And can life exist there? Maybe. And we're only talking about life being microbial life that you can see through a microscope, and no other life other than that. So this is what kind of things excite scientists when they have water vapor in a planet that's far away from us. Where there's water, there could be habitable conditions or could harbor something like microbial life. Could. K218b could potentially be covered in superheated, super-compressed seas where the water exists somewhere between liquid and gas, meaning you'd be vaporized if you tried to take a dip. So this is the size of it compared to us. We're not clear much about it. This is WASP, or wide angle spectrum photography. WASP 31b is really a hot Jupiter-type planet, about 1.5 times the mass of Jupiter. It's an exoplanet in the constellation of Crater, 1,300 light years away. Discovered in 2010, and orbits 4 days around its hot F star. So when it orbits that close around its hot star, it's a very hot planet. And this is one that was investigated by Webb this summer, which is very new information. This is WASP 96b. And it is 1,100 light years away. It's about a half-size Jupiter, but it's very warm. Very warm. It's kind of a steamy planet there, and in its atmosphere they found water vapor in its atmosphere. Is the slide up too high? I'm sorry, we need to adjust this. It's a little bit high for me to get this information.
That better?
A little bit.
That's about the best I can do.
Okay. Sorry for the interruption, guys.
There you go.
So it has water vapor in it, making it very warm. And there's a possibility of having water on it. That's how they see it with Webb information on it. Thank you. This is Kepler 78b. It's a super Earth-sized planet in Cygnus, 400 light years away, and it's bigger than Earth. It has no sister planets, but it's very hot. It orbits its star every 8 hours, which makes it very close to it. It's 40 times closer than Mercury is to our sun, and therefore its surface temperature is 3,000 degrees, stripping any stable atmosphere from it. The rocky world is a hellish inferno. So this is not good for habitability either. So planets then, most of the planets that we're finding, this is Earth's planet, our planet size right here. Most planets that we're finding are bigger than Earth, between 1 to 4 times bigger, mainly about 2 or 3 times bigger than Earth, and most of them have orbital periods that are from 5 days to about 100 days, where ours is 365. So that's what we're finding, but not that many of the big ones or even larger ones. And that's the tendency that this is going toward. So we talk about super Earths. They are bigger, more common than Earth itself, and astronomers are discovering more of the billions they think are out there. So super Earth is any rocky planet that is bigger than Earth and smaller than Neptune. In other words, it's a more robust Earth, what we're finding. This is, excuse the Star Wars reference, Tatooine, or K1647b, was discovered in 2016. It's a gas giant that is 3,700 light years away from us. It orbits 2 binary F-stars once every 3 years. So it's rather hot because it has 2 suns at its horizon. It's twice the size of Jupiter. It means it's a large gas giant. And it has 2 binary system, which is what many star systems have. This is Beta Genorium B, is 2.5 times the size of the planet, size of Jupiter, and it orbits an orange giant star called Pollux, which forms in the constellation of Gemini. It's 34 light years from us, and can easily be seen in the nighttime sky that is its parent. So it's right here. So we're talking about sizes of the planets and suns. You can put 1,000 Earths inside Jupiter, and a brown dwarf is 75% the size of our sun. It's a big gas giant. And the low mass star that we saw is with Alpha Centauri, a red dwarf, which are about 60% of all stars in our galaxy are red dwarfs, and our sun, a medium-sized star. This is a world that constantly is on fire. This is 55 Canceri E. It is 50 light years away, and this planet orbits 1.5 million miles from its sun. It's very close to it. And this planet is fascinating because it's tidally locked into its sun. That means one side is always facing and constantly facing its host sun, like the moon is to Earth. So this is very hot there. And what's going on is that the one side that faces the sun heats up, and the lava on the surface, and it has a thin atmosphere, lava droplets, and as rain on the surface. And the other side of it, which is the dark side of it, is cold actually. So this is what tidally locked means. We'll get into that feature in a bit. This is Kepler 22b. We're excited about this planet because it's about 2.5 times the size of Earth, but its surface temperature is 72 degrees. That's one of the holy grails of this. And it is 2.5 times the size of Earth, and it's tipped on its side, kind of like Uranus is, same thing with Uranus. That means one pole is always facing the sun for 6 months, and the other side then, of the other south pole, would face it for 6 months also. So it's tilted on its side. And if you were to put this where it belongs in our solar system for a comparison, it would be between Venus and Earth, which is in the habitable zone we're getting to, and it's 600 light years away. We don't know if it's rocky, gaseous, or liquid, but it's in that zone and much larger than Earth. This is HD 8512b. It's 3.5 times the size of our planet, and it's 35 light years away in Vela, but its surface temperature is 77 degrees. This is because it's in a more habitable zone away from its host star, like we are from our sun. This is one that Webb found. This is HD, read the numbers, a gas giant that is 64 light years away from us, whereas extremely high winds and temperature causes it to rain glass shards. That's fascinating. And another one Webb found, this information just 6 months old, is about 15 to 20 million years old. It's a very new exoplanet that's 6 to 12 times the mass of Jupiter, and this is what Webb found in the infrared that sees through the dust and gas of the planet. It's a new one. It's just made the news. This is another one that just made the news, WASP 39b, a couple hundred light years from us. And in the atmosphere of this planet, they found carbon dioxide along with water. Those are good things to know. It orbits a star in a more habitable way, in a more habitable zone. So this is new also. It has CO2 in its atmosphere. And another one that Webb found is this one. This number here is a gas giant. It's 2.5 times the size of Jupiter, and takes this kind of amount of days to complete one orbit. That's good because that's more Earth-like, and that's what they are looking for, how fast it goes around its host sun. So there are 4 different types of exoplanets we have seen. A gas giant, composed mainly of gas. A Neptune-like, a gaseous world around the size of Neptune, but smaller than Jupiter. Super-Earths, a potentially rocky world larger than Earth, that may or may not have atmospheres. And terrestrial, a rocky world that may or may not have oceans and atmospheres. And we talked about these two here, compared to Earth. As you can see, Earth will always be a bit smaller than these planets that we're talking about. So the assembly line of planets, which means how this is made, if you take a rocky core, not a surface, and then add a lot of gas and heat, you're going to get mini Neptunes. And if you have added more rock and less gas, you're going to have super Earths. So as we can see, compared to Earth, these are some of the exoplanets that they've found compared to Earth, and you can see ours is smaller. Ours has a radius of only 8,000 miles. So if we're talking about habitable planet criteria, well, what exactly is that? First of all, it concerns the Goldilocks distance, magnetic field, sun's force or sun-like star, the ozone layer, atmosphere, pressure, surface condition, and gravity. We are looking for the Goldilocks planet that's just right and in the habitable zone. And it's clearly obvious to anybody in this room, if you have planets that are too close to a star, it's too hot to have anything habitable there. And the just right would be in a more medium way, what we have in our planet, and too far out from its host star would be too cold. So in other words, the just right planet. Now, our zone here of habitability in our solar system is between Venus, which is 64 million miles from the sun, and Mars, which is about 150 million miles from our sun. So we have an 80 million mile habitable zone that water could exist on, in its atmosphere or on the surface. So we are the only planet that has water in its three states, solid, liquid, gas, and because of the way this is. That's what we're looking for, water, which can exist between about in the mid-30s Fahrenheit to about 200 degrees or around that area. So obviously, any planet too far away from its host sun will be too cold. An ice planet made of frozen nitrogen, frozen methane, frozen carbon dioxide, or dry ice, and water. And like Pluto is, by the way, the same thing. And obviously, too close to the sun will have a lava-type world where it's very, very hot, and it's in the thousands of degrees. Now, also it depends on the size of what we're talking about. We usually want planets that we're looking for between 1 to 2.5 times the size of our planet. Jupiter's diameter is 43,000 miles compared to our 8,000 miles. And again, we have a G-type star, or it's a smaller dwarf actually, and there's smaller ones, an orange dwarf and an M-type we saw in Alpha Proxima. So our sun is here, and the smaller suns procure more rocky worlds, and the hotter suns, the larger suns, procure more gaseous worlds. So there are larger suns than ours. We're talking about than ours, an F star, an A star, or B star. Let's take a look at that. So we have stars that are extremely big, like Antares, which is thousands of times bigger than our sun. Betelgeuse the same way, where our sun is just a dot here. And there's one sun that's 750 million miles in diameter. If you were to place it in our solar system, it would stretch beyond Jupiter's orbit. This is in our galaxy. Imagine a sun that big. It just dwarfs anything we can think of. And it's obvious to anyone in this room also that the habitability zone, or the green area here, can be further out for a hotter star and more closer in for a sun-like star that we have. And for cooler stars, the habitable zone could be in closer to it because it's cooler. And also this depends upon the star itself. Is it consistent? Does it dim and fade like every couple of weeks or months, like Cepheid variable stars that do this? Or does it conk out after, does it dim after about 3,000 or 4,000 years and leave its host planet in a state of an ice condition, of an ice age? But ours has been consistent and has been doing this for 4.5 billion years. That's why we have this kind of habitability thing. So the star has to be consistent in its output toward its host planets. And Kepler and these other telescopes can't tell if there's a magnetic field. These are conditions for habitability. doesn't have one. Well, we have a robust one because our planet has a solid inner core surrounded by molten iron and nickel. This produces a dynamo, an electrical field. And because of that, it then protects our planet from being bombarded by solar wind or highly charged particles from the sun. So it acts as a shield, mainly like this. This is what this does, and it looks like this. You can see the magnetic field, and you see the aurora borealis when the particles are interacting with our magnetic field in the north and south poles. So that's why our planet is protected, but we can't tell if that's going on. We can't tell because we don't have instruments for this. However, if a planet does not have a strong magnetic field, then what happens is all chaos breaks loose. Mars doesn't have one. And why? Because 3.5 billion years ago, the inner core of Mars solidified. It stopped being a dynamo. It stopped. And therefore it solidified, and then the magnetic field stopped being produced. And because of that, then the solar wind blew and hit the planet, and at 5 grams per second, knocked into space all the atoms of hydrogen and nitrogen and carbon, because Mars once had an ocean the size of the Atlantic Ocean. So where did all those atoms go to? Well, they went out in space. Well, let me digress a minute from what I'm trying to say. What happens when these things go out in space? So these atoms, they don't have a shelf life. They're not because they're not alive. They've existed for at least 10 billion years. So they drift out in space for tens of millions, hundreds of millions of years, or even billions of years, and sometimes these atoms then come in contact with where new stars are being made, like in the Pillars of Hercules here in our galaxy, and they help seed and nucleate these areas with new atoms to build new planets and new stars of carbon, of hydrogen, of helium, of nitrogen. That's where they go. And the same thing happens when the outer shell of a sun explodes, called a supernova. It'll leave a nebula or a ring that'll expand out in space. And sometimes this expansion then bumps into areas like this and helps seed these areas. So it is possible 4.5 billion years ago, when our solar system was being made, that a planet could have had its atmosphere taken away from it because it lost its magnetic field. And it blew all those atoms. They came into our area when our little solar system was being formed. So it could be the case that we have atoms in us, because we're made out of water, H2O. We could have hydrogen and oxygen atoms from another planet. What goes around comes around. Nothing can be created, nothing can be destroyed with our universe. Now, I digress too much, so let's get back to Mars. Because it lost its atmosphere, it turned into a dry, desolate, barren, frigid desert. It has been that way for 3.5 billion years. We have robots on there looking for fossilized microbial life, but they won't, the chance of them finding it are less than 1%, but we're trying. And there's also another feature Kepler can't discuss, can't get too much of. It's about an atmosphere. We get a little bit of information, but too much carbon dioxide in the atmosphere can lead to a runaway greenhouse effect, like on Venus. Billions of years ago, Venus's oceans evaporated, and it built up a huge layer of carbon dioxide. So the sun's heat is able to get inside this, but can't come back out. It can't be radiated off like it is on Earth. So therefore, it gets super hot on Earth. This CO2 acts as a blanket and keeps it all inside the planet. Therefore, Venus becomes the hottest planet at 870 degrees, even hotter than closer in Mercury to our sun, and it consists of this kind of atmosphere, which is a runaway greenhouse effect. And therefore, you can't see the surface of it, so it makes sense that you need to have a radar map, like we do on Venus. Not quite this color, though. It snows metal and rains sulfuric acid on Venus. So we can't get that information, and maybe planets need to have an ozone layer on it in its upper atmosphere, like we have here on Earth, that protects us and acts like a sun shield from the sun's harmful ultraviolet radiation. Our ozone layer protects us against the UVA rays, UVB rays, and protects us against this. But not on Venus or on Mars, they lost their oxygen layer. They lost it. So how would you find that? Is that ozone is a molecule with 3 atoms, and what makes the ozone layer. And it's really a waste product that's given off, oxygen is, to produce ozone from really plants and vegetation. So this becomes an invisible and necessary umbrella that protects life. So this is a good thing to have. And when we go to Mars and live there, we go to the moon and live there, there's nothing to protect us against the sun's ultra damaging rays, so you might have to live underground. You know, take away kind of the beauty of living there, right? And then if a planet maybe is tightly locked to its host, like the moon is to Earth, due to its close proximity, the planet rotates around its sun at the same pace that it orbits it. Therefore, the planet will show only one side of its face to its parent. So, if it's tightly locked, one side of it might have liquid water, but the other side might be in ice because only one side is locked to it, like the moon is to Earth. That's why the moon, whenever you see the sunny part of the moon, it's 250 degrees. When they went up there in the astronaut suit, they had the air conditioning because it's so hot. But on the opposite side of the moon, the dark side, it's negative 250. We don't have things that work too well in that. Just think about where you're in your hometown where you used to live. Nothing worked below 0 anyway, did it? Okay, so tidally locked Cancer E is like this, Cancer E. It's really close, and one side faces it like we talked about this hellish world before. And there's a different situation, but it's a little bit has the same kind of effect. It's called tidal heating, and Jupiter has with some of its moons. Jupiter really is a big gravitational well, kind of like a big well, and anything that comes close to it, it plays havoc sometimes with any kind of moons next to it. In other words, as Io travels around Jupiter, what happens is a lot of tugging and pulling on the inner mantle of the inside of Io, causing internal hemorrhaging, causing it to be viscous and liquid, causing it to have eruptions. And when you can see an eruption from space, it's 3,000 miles away, that's a big deal. So it might have tidal heating on it, which we'll get to also with some of Jupiter's moons. In the futuristic movie Interstellar a few years back, a potential planet that spacefaring astronauts were looking for had a large ocean on it, but was so close to its star, massive tidal waves regularly occurred there. A tidally locked planet is not a good habitability feature, even if you have water on it. Who'd want to deal with 200-foot waves? Also, we can't measure this too well either. There's also pressure on the surface of a candidate planet to consider for habitability features. Our atmospheric pressure is 15 psi. But on Venus, it's 92 times that of Earth, or 1,300 psi. That's because all the big layer of atmosphere is pushing down on the planet. It actually makes the surface features on Venus actually shrink down because it's so heavy. So when we try to land a probe on Venus, what happens to it? It's twice as hot as your oven, it gets melted, and it gets crushed at crushing temperatures. And also about surface conditions that exist on planets. Rocky solid type planets are the best candidates here. But maybe the planet is covered in craters, like it is for Callisto and Ganymede, moons of Jupiter. How totally covered are. Maybe, like on the moon of Saturn, which is called Titan, we sent a probe there. It's filled with, it's about 200 degrees below 0, and filled with liquid methane, has lakes of that, liquid nitrogen, and it's very cold there. We sent a probe there. It didn't last very long. So this moon has an atmosphere, which is the only moon that does in our solar system. And we're going to send a probe there called Dragonfly at the end of this decade. It'll have 8 rotors on it, be nuclear powered, will land on Titan on a parachute, and then take reconnaissance flights around. Won't that be interesting? It'll be on the SLS, by the way, when it goes up one day. Now we're going to get into solar systems. Instead of just one planet, there'll be solar systems, there'll be more than one planet. First one is a little bit hyperbole. There is about, it is PSR B1257, called Poltergeist and Phobatar. Again, they had these names because they were so excited about what happened. And they're planets that orbit a neutron star. And a neutron star is an F-sized star, a bit larger than our sun. The outer shell blew away, and what you have is a core. But the core is very, very compressed because all the protons and electrons have been squeezed out of it, and what's left are neutrons, which can be packed in very closely. And this is extremely heavy. It's about the size of Manhattan, about 12 to 15 miles in radius. It isn't very big, but it's powerful. That is, it's heavy, so a fistful of this material will weigh as much as Mount Everest, 1 billion tons. And will have a surface that has an atmosphere of 4 inches thick, and it's made of liquid diamonds. It's so heavy that you can't, if you land on it, you'll never be able to get off because the escape velocity is 90,000 miles per second, where our escape velocity is 8 miles per second. So we have these two planets going around us, and by the way, it has these lines on it because the neutron star spins thousands of times per minute. When that happens, any atoms on there get excited and gravitate to the poles and come out shooting out of the poles, and when it twists and turns like this, it comes out as light beacons toward us. So that's a fascinating way to talk about it. But the planets around it, Phobatar is a super Earth-sized planet orbiting this pulsar right here. And it's quite big. It's 2,300 light years from Earth in Virgo. It's a couple times the size of our planet. And it was one of the first planets discovered outside our solar system. Its temperature is 28,000 degrees at least, and orbits its star every 98 days. So it orbits this pulsar star, and it's extremely hot as it receives deadly amounts of UV radiation, and particularly gamma rays and X-rays from this pulsar star, sometimes known as magnetars. But its sister planet is Poltergeist, and this planet is 4 Earth-sized big and is much larger than its sister, and orbits its planet its star every 66 days and is close to its sister. So we see two bizarre worlds far away in a strange solar system. Now we'll talk about different solar systems that are more normal-like. This is Kepler 186. This will be the sun, but it'll have very close-in planets like B, C, D, and E that are not in the habitable zone, the green zone here, but the one we're interested in is Kepler 186f, which is a little bit bigger than Earth. And, excuse me, this orbits its star once every 130 days and is the outer edge of its habitable zone. Its sun, though, is like ours, but this planet only receives 1/3 the energy we get from our sun. Standing on the surface of this planet, and it would be very dim, even though it's about the size of Earth, which is what we like in terms of habitability features. So the brightness of its host star would appear as bright as our sun 1 hour before sunset. In other words, it's a very weak star that we see here. It would be very dim there. This is Kepler B and C. Kepler 36 is the sun, B and C are its planets, and B is right like this. The inner planet, Kepler 36b, is a rocky planet that is 1.5 times the size of Earth and orbits its sun every 14 days. So B is very close to its sun and very, very hot. Whereas further away sister planet, C, is further away and is like a hot Neptune. It is 4 times the size of Earth and weighing 8 times as much. So these planets are in conjunction with each other, they're a bit locked. And if you're standing on B, this is what its larger sister C would look like. And this would be C, the larger planet, and B, the smaller one. And what's interesting about B is that it's tidally locked to its sister and to its sun, but particularly to its sun. And we might have a lava-like world there, where this kind of surface, and the other side of the planet, the smaller one, C, might have ice on the back of it and be very dark. This is the TRAPPIST-1 system. This is one of the holy grails when you talk to a NASA scientist of what they like the best. This is a system that's 40 light years away in Aquarius and discovered in 2017, and where 7 Earth-sized planets closely orbit around a cool dwarf star. So we have planets that are very Earth-like, terrestrial, and a couple of them are not in the habitable zone, but a number of them are. So if you were to put this in our solar system, it would fit well within Mercury's orbit. Remember, Mercury has an orbit of between 29 and 41 million miles from the sun, so this is very close. So they're all close together, which is what we like, and they're Earth size. And if we take a look at some details with them, we'll find out that the orbital periods are really whizzing around the sun really fast, like 1.5 days, 6 days, 18 days. Their radius, that means 1.0 being Earth, is about the same as Earth, as you can see throughout the 7 planets. But their density is lower than Earth, and that suggests to me 3 things. First of all, it doesn't have much iron in its core, and also could be tidally locked, and therefore taking away its magnetic field. So we're learning more about this system, but this is the one that they like because of the proximity to Earth's size that it is for these 7 planets. This is the Glass System 581, discovered in 2007, and it's got 7 planets that revolve around its host, which is a red dwarf star in Libra, 20 light years away from us. So we're interested in C because it's about the size of Earth. It's pretty close into its sun. And we're interested in G because it's the same orbital period as Earth has. This is why we're interested in the system. And 581c, by the way, right here, is 3 Earth sizes big. It's a super Earth, and it takes 13 days to orbit around its parent star. And so this is what Earth is compared to C, and Earth is compared to G, which is more of a zone that we are with our planet toward our sun. And if you compare the 2 planets with G, it would look like this. So they're interested in this system too. Again, as you can tell, the proximity is important, being to favor liquid water. This star does not have that kind of water on it. This is a star system in Lyra called Kepler 20a, which is the sun. We're interested in Kepler 20e and 20f being more Earth-like, but however, 20f takes 20 days to orbit its sun, which means it's really hot there. It's about 800 degrees Fahrenheit, and you can all fit this in within the orbit of Mercury. So we're seeing a lot of star systems then that have very close-in planets that are close into our sun, not like our solar system. And this would be Earth compared to 20F, about the same size, but very hot. And Kepler 20F compared to Earth compared to 20E, but being hot. This is the Kepler 62 system. It'll have 5 planets in it, 3 not in the habitable zone, B, C, and D, but E and F are in the green habitable zone, which is why we have a fascination for this one. And Kepler 62, is a 5-planet system and 1,200 miles away in Lyra, 500 light years away. This planet orbits a dwarf star that is 7 billion years old and 2/3 the size of our sun and 1/5 as bright. So it's in the habitable zone, these 2 planets. And this is Earth compared to 62F and compared to 62E. And we talked about this one before, more of a Neptune size. This is a crowded alien solar system known as KOI, Kepler Octative Interest 500. It'll have 5 planets on it, though bigger than Earth, as you can see in diameter. And its orbital period is also very quick, 1 to 10 days going around its star. All could fit in within the orbit of Mercury. So that's what we're finding. And it's I forgot how far away this is. 1,000 light years away from Earth, thank you. And the Kepler 11 system, it'll have Kepler 11a, and then B, C, D, E, F, and G. And these planets can all fit within basically the orbit of Mercury, so they're all very hot and very close to its sun, but they're a little bit more terrestrial. This is Kepler 47 system, and it will have 3 Neptune-sized ice planets that orbit a double or binary G star in Cygnus. And one star has our sun's mass, with the other one being a dwarf star, 1/3 our sun's radius. So they have a binary system. 47b and c have low densities and milder temperatures, thought to be uncommon from our experience. 47b takes 50 days to orbit because it's close in and not in the habitable zone. It just takes 50 days to orbit its sun and is over 3,000 light years away. But C is in the more habitable zone, but it's a gas giant. Might or may not harbor water in it. So, and then lastly we have the Kepler 90 system, which is kind of like our solar system, but much bigger planets than Earth, which is 9 planets away, about 1,000 light years away, 2,500 light years away in the Draco system. Okay, so obviously, summing all this stuff up, it's clearly obvious that we're going to need to rethink the way solar systems are developed. Not all, obviously all of them are not like ours, and we need to get rid of the Bode's law. In our solar system, there's a mathematical correlation between the planets. It's a simple rule that gives the distances of the suns from our sun. The formula suggests that extending outward, each planet should be approximately twice as far from our sun as the one before. So there is a mathematical correlation, but what we've seen clearly isn't the case in many of the solar systems that I've shown you. This is how they found Uranus in 1787. William Herschel did that. So this is we have 190 moons in our solar system, so it makes sense that the planets that we're seeing would have moons too. But we can't tell that from Kepler. One day we'll be able to. So if that's the case, well, we need to rethink about moons too. And this is a PDS system 70 in Centaurus. It's a ring-shaped area that's a disk made up of dust and gas, and will start to spin and then coalesce due to gravity, and future moons can form. This is the way some of them are formed. Our moon formed from a giant asteroid 4 billion years ago called Theta that hit the Earth and was absorbed into it, and our planet was molten at 4 billion years back, so it threw a lot of the molten material up into space and circled around the Earth, and had a ring around it, started to coalesce to be the moon. And speaking of moons, this is Jupiter's moon called Europa. It has an icy surface shell on it that's 10 to 15 miles thick, and beneath this, by the way, it might have a double ridge system on it that have pockets of water in it too. And beneath this giant thick ice crust that's quite thick is an ocean world. And it's considered to have as much water as all the Earth's oceans combined on this moon. Now, with the constant pulling and tugging of its massive parent Jupiter that would produce, it would cause tidal heating, maybe on the inside of Europa's solid core. In other words, there's a lot of internal hemorrhaging going on. This might produce heat. And at the bottom of this ocean, it might have hydrothermal vents that exude hot water, which circulates in here. There's a mission called Europa Clipper that at the end of this decade that will confirm this, going around the moon 45 times. So it might have these hydrothermal vents. It might, and on Earth, we have these hydrothermal vents, and and these vents could be like the ones found in our ocean. They spew out hot water, gases, and minerals like on Earth here, even without sunlight, as they are a magnet for carbon and sulfur-based microbial life. So this moon greatly excites scientists because where there is water, an energy source, and organic compounds, microbes can exist. That is the building blocks for biological processes. Same is true of the moon in Enceladus, where a large ocean 6 miles deep exists beneath a thick, frozen, icy crust. And what's going on in Enceladus, and it's fascinating, is that there are geysers at the South Pole that spew out water at the rates of 400 cubic feet a minute, 400 cubic pounds per second from cracks on its moon, on the South Pole area, where the ice is thinner. And this is what it looks like from space. These are actually pictures. So it's able to do this, and that's how we know there's an ocean underneath this thick crust that some of this has. And again, it could have hydrothermal vents on them, and then expelling this, making the water warmer and expelling water out. In other words, they go through cracks and shoot out at the surface, or it goes into space and then falls back as snow on the ground, on the surface of the moon. Looking like this, looking like this. We sent a probe to these plumes 11 years ago, and they made of water. So this excites scientists, and I'm not too far from being done, because other planets, other solar systems might have an asteroid belt like we have here in our solar system, made up of rocky debris, planetary leftovers that circle around. There are trillions of them that do this. And inside of that, we have dwarf planets like Vesta and Ceres inside this kind of asteroid belt. And if it has an asteroid belt, well, it might have a Kuiper belt like we do, an outside area where there's a lot of jetsam from unwanted, rejected, and broken up material left over from the solar systems. And this Kuiper belt is two things: where Pluto exists, and New Horizons found this kind of shape, this kind of a small planetoid out there. And this is where comets originate from, the Kuiper belt, and they go around our sun once every couple hundred or a couple thousand years. And these comets are obviously frozen water. And sometimes they hit other planets, and this is one theory of how planets get water on them. How does water get on planets? Well, they could be hit by comets. On Mercury, there's enough water on, there's 1,600 cubic square miles of ice on Mercury, the closest planet to the sun. It's hidden in craters and in areas where, in the poles, where it's not very hot, or not as hot. And this is called exogenesis, or exohydration. Exohydration, actually, from when comets hit planets and give them water. And that's how we think we have got water on our planet. It's got to start somehow, right? You can't get nothing from nothing. Something has to start. So we have that. It might have an Oort cloud, and even further out section, other than the Kuiper belt, with more broken up flotsam and jetsam from this. To test that there's water on the moon, because we're going to be living there one day, we're going to send the probe Viper out there, which is remote controlled, and searching for water in craters and water where we can get it, because you have to have water. Because it takes $150,000 to put 1 gallon of water on the moon. That's why. And this is the James Webb Telescope. It'll have a 20-foot mirror on it, like we talked about before. And this is what's getting us information. And so these are some of the planets that we found compared to Earth, all very larger than Earth. And lastly, in the center of our galaxy is a giant black hole called Sagittarius A. And what a black hole is a core of the sun that's 2.5 times as big as the size of our sun. And the outer shell explodes into supernova, and what's left is a core. The core implodes to become a singularity, or a point of infinite density. And then it starts to absorb in a lot of dust and gas, and it gets larger, especially in the center of galaxies, because in the center of all galaxies are galactic black holes. Ours is 4 million solar masses big, and it has an accretion disk on the top of it that swirls around and emits light that is 15 million miles across, and exudes information, and exudes light from it, actually. So it circles around and exudes light from it. It's in the center of our galaxy, and there's one in the center of all galaxies. That's why we look at pictures of all galaxies. They're very bright in the center. That's why, and they produce tremendous amounts of energy. Although our black hole isn't very hungry these days, it's kind of in a dormant stage. So we're all looking forward to the day when we're able to land on other places as the future awaits. And thank you. That is the end of this time. Thank you.